In this lecture, I will go over the first classical analytic method for solving first-order differential equations, certain first-order differential equations. And this is called separation of variables and applies only to equations that are called separable. A first-order equation, this only applies to first-order equations, but this equation is called separable if you can isolate, so you isolate the first derivative on one side of the equal sign, and on the other side you'll have only this function of y and t, but you can divide that into some function of y times some function of t. That's separable. Here's an example. So I have dy by dt equals t cubed plus the sine of t. Okay, in a sense that's separable, but there's a few issues with that, because here is your function of t multiplying, oh no, I meant y. Here's your function of y. This is not separable. That's the problem. Okay, the addition sign there. You can't write it as two functions multiplied together. So you start like this. dy by dt equals this function of y times another function of time. And then when you separate them, this is where we're getting the name separation of variables, you pull, good grief, you pull this function over to the other side. So you end up with 1 over h of y dy by dt equals g of t left over on the right hand side. Be sure to specify h of y not equal to 0. That's a proper way to do it because you cannot divide by 0, as you know. The textbook doesn't do this, and here I am criticizing the textbook again. I can only imagine what they have to say about me if they cared to do so. But they do not specify that h of y cannot be 0. As a result, they have a whole section in this chapter called missing solutions. This is the missing solution. Okay, so you don't need that chapter section on missing solutions. If you include that exactly, you can then go back and look at the emphasis, or the importance, I'm sorry, of h of y being 0 and see how that affects, or how that is part of the solution set for this differential equation. So let me give an example here. If I had dy by dt equals, say, e to the minus y times t squared, that's separable because I have two functions multiplied together, one only of t, one only of y. Now when I separate them, I have to bring the y term over to the other side. That would be e to the y dy by dt equals t squared. Now the variables are separated. It's also possible that you can separate variables when the function g of t is only 1. For example, if I have dy by dt equals y cubed, when I separate the variables, I get equals 1. It's okay that this is a constant. Okay. Now I'm going to derive the method, and the reason for doing that is, well, for completeness, and also because the method looks like it has some funny business in it. What we do after we separate those variables is integrate both sides with respect to time. So right here was the separation, and now you see we're going to integrate both sides with respect to time, and the bottom line is going to be here. So we're integrating the function of y with respect to y and the function of g with respect to t. This is how we solve that. This is the end result. it looks suspiciously like to do that we cancel the dt's, but you know that you cannot cancel dt's. d by dt is an operator, and you don't cancel the dt by multiplying by dt. So I want to show the steps so that you can see that it is a valid method. Alright, so we have the first step where we integrated both sides with respect to time. Then we write out the t dependence of h of y. So h of y is really h of y as a function of time, dy by dt times dt. Now I'm going to change a variable. I'm going to let u equals y equal to y of t. Then what is du? In a change of variable form, we write this, although you might say that just contradicts what I said a minute ago, but that's how we do it. Okay, du equals dy by dt over dt, so I can replace all of this with du, and of course I replace the y with du in the change of variable. So let me erase that for a second, and I'll write it again. So now I have the integral of 1 over h of u du equals the integral of g of t dt. And now I do another step which might look like a sleight of hand, but isn't. Any variable under an integral sign is a dummy variable. That means it doesn't matter what it is. You've encountered this before. If I have an integral, say from 0 to 5 of t squared dt, that's fine. Now if I change one of the limits of integration to be t, I can't use t under the integral sign. I change that, for example, to ta. I could have changed it to x. Doesn't matter, because the variables under the integral sign are dummy variables. They're going to go away, essentially. So with that in mind, I change the dummy variable, I change u in this equation, I change that u to the y. It's just any old y. It's not y of t from the solution, it's just y, although the solution is going to fall out from that. So that's all I'm doing, is really changing variables. And now I have the integral of, well, equals the integral of g dt. I'm going to run through an example, and it's going to show some principles of solving using separation of variables that are handy. So what I'll use for an example is the equation for first order kinematics in pharmacology. This is one model of the elimination or the digestion of any substance that's put in the body. When you eat something or you take a drug or something is injected in you, it doesn't just stay in your body, otherwise it would build up and kill you. It gets digested or converted into something that can be eliminated, and that's usually done in the liver, can be done in the lungs, kidneys, a little bit. Okay, and the constant K is this clearance rate. Let's just say it's how it's cleared by enzymes in the liver. Okay, R is a rate, we'll say it's injected, something that's being injected into yourself or to a patient. C is the clearance. Oh no, I'm sorry, C is the concentration of the substance in the blood. So C is how much you have in the blood, say, I don't know, micrograms per milliliter, something like that. And you're watching that at time. R is a rate that it's being injected, and this is not varying with time, it's just a flat rate. So you see this is a constant. And K is a constant also. In truth, these would be functions of time if you were really solving this problem, but we're going to use them here as a constant. Now, it's an initial value problem. First order equation needs one initial condition, and we have it. Okay, is this separable? It's separable because there is no function of t alone, so I can let t be 1, just like g of t be 1. Remember, here is what it looks to be for a separable equation. dy by dt equals some function of y times some function of t. So I'm going to take all this as a function of c. C is now my y, and g of t I'll let be 1. Okay, so here's what it looks like when it's separated. And of course we want r minus kc not to be 0 here, and we'll see how that plays out in the solution. Now I'm going to integrate both sides, but remember we had a conclusion in our method. So I'm going to be integrating 1 over r minus kc with respect to c, and I'll be integrating 1 with respect to t. Actually, I am integrating both sides with respect to time, but by the steps above I've changed this time integral into an integral with respect to c. Now the next step is to isolate c, but c is buried here in a logarithm. I'm going to isolate this because that will be my solution. That's going to be c as a function of time. So to do that, I'm going to use exponentiation. First, I will make this only be the natural log, so I'll put the minus 1 over k to the other side. So I'm going to write natural log r minus kc equals negative kt minus ka, and just leave it like that for a minute. Okay, I ran out of room, so I have to rewrite this. Okay, so I have here natural log of r minus kc equals minus kt minus a times k. Alright, now I'm going to raise both sides. I go e to the all this, e to all this. Okay, e is the inverse of log, just like log is the inverse of e, so this side only becomes r minus kc, and now I have a chance to isolate the c. On the other side I get, well, I can write this as two functions, which is what I want to do right now. E to the minus ak. Actually, I didn't intend to erase that, so I have to write that again. K, no. R minus kc, which is a function of time, equals e to the minus ka, e to the minus kt. Okay, now I will isolate the c. C of t equals r over k minus 1 over k e to the minus ka e to the minus kt. Now I'm going to do another step of combining a lot of constants into one. So all of this that I've highlighted here is a constant. It seems a little strange to take a constant from the problem and wrap it into essentially a constant of integration, but it is okay to do that. So now I get a solution that looks like this. R over k, and it doesn't matter if it's plus or minus, I'll just say plus a e to the minus kt. So there's my general solution. It is from a first order differential equation. It produced a one parameter family of solutions. The one parameter is the a in this case, and there was one initial condition, and a can be evaluated based on that initial condition. So I will do that now. So I have something that looks like this: r of k plus a e to the minus kt. My initial condition was that at time 0, when I started this experiment, the concentration was some C0. So that's some initial concentration in the blood when you start the experiment. So if I put the 0 through this equation, I get R over K plus A e to the 0. E to the 0 is 1, so I'm good. Now I can solve for A. A is going to be C naught minus R over K, and here is my solution. R over K plus C naught minus R over K e to the minus KT. Okay, if you put T of 0 here, you can see that you'll get the C naught back, which is what you were supposed to do. Now let's analyze the solution, and we're going to see terms here that we're going to see over and over again in solutions. We're going to see what is called a steady state term or an equilibrium term. In this case, it's R over K. It's called steady state or equilibrium. Well, let's just call it steady state for right now, because it doesn't change with time. R over K is just R over K. The next term that we have is called a transient term. It's transient because it changes with time. It's also transient when you think about it, because e to the minus k t is vanishing. It's going away. So in that sense, it's transient. In some solutions, people don't bother with the transients because they occur so quickly that they aren't of interest to their device or their experiment. But of course, we're going to include them here, and we have to know about them. So here's the transient term right here. Now recall from the step where we separated the variables that we said that R minus Kc could not be 0. That means C could not equal R over K. Well, here's an R over K in the solution, but you always have this transient term because the transient term never goes away. E to the minus t never goes to 0. So what we have plotted out here, what we will plot out here in a minute, are all sorts of solutions, but this term, when C is equal to R over K, okay, let me say this again. C equal to R over K was not used to derive this equation, but C equal to R over K is a valid solution. It just had to be handled separately. Again, the book calls that missing solutions. It's not missing, it just has to be handled separately. What happens when C is equal to R over K? To see that, I'm going to write again the differential equation. dc by dt equals R minus Kc. So when C equals R over K, the derivative is 0. When a derivative is 0, that means you are at an equilibrium solution. Often it's written with a subscript. R equilibrium in this case is R over K. If you start your experiment on an equilibrium solution, you will never move off of it. Equilibrium means you're just going to stay there. You're actually a steady state situation. And the reason you're not moving off of it is because the first derivative is 0. If the first derivative is 0, there's no change. If there's no change, you're not going anywhere. You're going to stay right on equilibrium. So we do see this equilibrium solution here. However, you're never going to be there unless you totally ignore your transients. So you're pulling information out of the solution, but it is not, in a sense, a solution of the method. Now here are graphs of some of the solution curves. Here is that equilibrium concentration. This was the solution that we eliminated when we did the separation of variables. And when we look again at it, we find that it is indeed the one that is the equilibrium solution. If you start here, you never change. Another way to think of this, or another example, is Newton's law of cooling. If you look at the temperature in Newton's law of cooling, it says that the rate of change is going to be some constant, I'll say K, TA minus T. Okay, TA is the ambient or room temperature. So if you take a bowl of soup and it's exactly at the room temperature and you set it on the table, it's not going to get hotter, it's not going to get colder, it's going to stay at the ambient temperature. That is the that's the equilibrium solution. And you see that would set the rate of change of temperature to zero. T equilibrium is the ambient temperature. If you start this bowl of soup and you put it on the table and it was hotter, and it's, in a room that has a lower temperature, it's going to cool down. If you pull it out of the refrigerator and put it on the table, it's going to heat up. And that's what we're seeing here with this concentration. Here's equilibrium at R over K. If you start your initial concentration was here, so you have a substance that's very highly concentrated in the blood and you start injecting it at a fairly slow rate, shall we say, compared to the clearance, then it will gradually asymptotically approach the equilibrium concentration with time. If you start the solution here where you have a very low concentration, even say 0 in the blood, and you start injecting a substance, it will gradually move up and asymptotically approach the equilibrium concentration. Now remember, these are unique solutions, and they will not cross. You'll never cross into the other area by this method. Could a person potentially do it not by this method? All right. So how would that happen in reality? Well, K and R are really functions of time, and say you gave an extremely large dose, overwhelmed the ability of the liver to induce enzymes that would digest or modify the substance that you're putting in there, then you would suddenly go to a different state. So a more complicated model would model something else. But in the model that we have here, the equation that we have here, no, you will never cross over. You will always just either asymptotically approach equilibrium from below, or the concentration in the blood will decrease as you asymptotically approach equilibrium from above. So let's do a quick review of the method. You start with a differential equation, this will be a first order equation, and you find out that it's in the form of some function of y times some function of t, and that function of t could be 1. Right? Those two have to be multiplied together. So when you have it in that form, you're going to pull the h of y over to the other side, and then the g of t remains there, and then you integrate. You're really integrating with respect to time, but by some change of variables, you end up looking like you're integrating this way. So you'll have 1 over h of y dy equals the integral of the function of time times dt. You have set aside a special condition where h of y is not equal to 0, and that will be considered later. It's another solution, but it won't be a solution of the method. You carry out the integration, and then part of the steps in the integration is that you combine and simplify constants of integration. If you have two constants added together, for example, if you had, we'll say c1 plus c2, we just write them as c. If you have e to the ct, no, not t, if you just have, e raised to the c, then you just write that as c. You don't care that c constant is in the exponent, it's still a constant. Plus and minus signs can be changed into plus signs. The other point here is that, as this happens with this method, you're dividing by a function. If you divide by a function, you tend to get this natural logarithm, and to undo the natural logarithm, you raise both sides as exponents of e. So that's a method of separation of variables. It only works for certain equations that are first order equations that are separable. They can be nonlinear. Linearity is not needed here.